In this video, we are going to discuss the compression of an ideal gas under various conditions. So the setup of the problem is that we have 4 cubic meters of air at atmospheric pressure and at 300 Kelvin as its initial temperature, and that air is compressed to a final volume of 1 cubic meter. And what we want to do is we want to find the work done on the air as it is compressed. We're going to treat the air as an ideal gas, and because most of the air molecules are made up of nitrogen and oxygen, which are diatomic, we're going to treat the air as a diatomic ideal gas, which has 5 degrees of freedom. That is 2 rotational degrees of freedom and 3 translational degrees of freedom. Okay, and we're going to calculate the work that's done during this compression if we do it in 3 different ways. First, we're going to calculate how much work is done if it's at constant pressure, then we'll try at constant temperature, and then we'll try adiabatic compression. And adiabatic, again, just means that no heat flows in or out of the system. So there's no heat flow. Begin by looking at the constant pressure case. So if pressure is constant, our integral for the work is always negative integral of V initial to V final of pressure d volume. But since pressure is constant, we can just pull the pressure out front of the integral, and then our integral is just over dV, which of course just leads to V. Plugging in our initial and final volumes here, we end up with a work done of 303 kilojoules. Okay, if we do the constant temperature case, well, pressure is no longer constant, so we have to leave it inside of the integral. But we know that from the ideal gas law, pressure is nKT over V, right? We're just solving the ideal gas law, PV equals nKT. We solve that for pressure, and we end up with this expression here. Now, this is usable because everything except for volume is a constant. We couldn't do this if temperature for some reason depended on volume, but because we know that the temperature is constant, we can use this, and in fact the nKT just gets pulled outside of the integral. Okay, so next the integral of 1 over V is just the natural log of the volume here. And then carrying out our limits here, we end up with 560 kilojoules. I just want to note here that I used 2 little math tricks. One is that I said that the difference between 2 natural logs is actually the quotient of those 2 natural logs. And I took this minus sign and I moved it inside of the natural log, and that flipped the order, because having a coefficient out front is like having a exponent of -1. So the minus sign out here can actually be taken inside of the natural log and used as an exponent of -1. V final over V initial raised to the -1 power is V initial over V final. So that just got rid of our minus sign. We could have done it either way. And then the final math trick was that we realized that nKT is just P times V. Because T never changes, PV, that the product of pressure times volume, never changes. And so we can just use the initial pressure and initial volume here instead of nKT. We could have used the ideal gas law to calculate N and then found nKT, but it's slightly more efficient to just realize that this nKT is PV. And so we can just plug in the initial volume and the initial pressure because the product of those never changes as long as the temperature doesn't change. Okay, and that gives us 560 kilojoules. So at constant temperature, it's actually more work to compress the gas than it is at constant pressure. Now let's look at the case of an adiabatic compression. So in the adiabatic case, we can use the expression PV to the gamma equals constant. So this gives us a relationship between pressure and volume for adiabatic processes, which is exactly what we need if we want to find the work. where gamma is our related to our number of degrees of freedom. It's the F plus 2 divided by F. In this case, F is 5 because we have 5 degrees of freedom for a diatomic ideal gas. And what we can do is, because this PV to the gamma is a constant, we can say PV to the gamma at any given moment must be equal to the initial pressure times V initial raised to the gamma. And then we just solve for pressure and we get this here. And this is perfect to plug into our work expression because it has two constants. So this should have an initial on it. It has two constants, P initial and V initial, and then our variable that we're integrating over only. And plugging in for gamma is 7/5 in this case. Okay, so carrying out this integral here, we end up with V to the 2/5 on the bottom, and plugging in numbers to this expression, we get 749 kilojoules. Now, I just want to take a moment and say what not to do really quickly. So it might be tempting to say that your work is equal to negative integral of P dV, but I know that the pressure is NKT over V, right? I know this expression for the pressure, and why can't I just use the ideal gas and just calculate the work this way? This has a V in it. The problem is that the temperature is not a constant. This temperature here is some function of the volume. And because it's some function of the volume, we can't just pull it out of the integral. We need to figure out how it depends on volume, right? Which we could do. There is a relationship between temperature and volume for an ideal gas, which we could use in order to solve this integral, but you cannot pull the temperature out because it depends on volume. So this method doesn't make a ton of sense, and certainly you can't do it without explicitly finding the relationship between temperature and volume for an ideal gas, adiabatically compressed, which is, just for the record, given by T to the F over 2 times volume is equal to a constant. So it's derived from taking this expression here for pressure and volume, and then using the ideal gas law to change pressure into temperature. Now that we've found the work done when compressing the gas in each of these methods, I'd like to draw the PV diagrams for each and see if we can figure out why we're getting different work values for these different types of compression. So let's start with isobaric. That means constant pressure. Okay, so in our PV diagram, we're starting here at this initial state, and we're ending at a final volume, which is 1/4 of our initial volume. Okay, so the first way that we did it with constant pressure means that the pressure does not change as we compress our air. And so the work done is the area under this curve. Because we're compressing the gas, we expect that the work done on the gas should be positive, since we are pushing in on the gas and the gas is moving inward. So our force is in the same direction as the displacement, which leads to positive work. So this area here is the work done on our gas. Okay, quickly analyzing this, we can see that the pressure times volume here is lower than it is in our initial state, right? So if I look at this point, our final pressure final pressure times volume value is 1/4 of our initial pressure times volume value, because our Pressure hasn't changed, but our volume has dropped from 4 to 1, so it's 1/4 as large. Now let's use the ideal gas law to figure out how the temperature of the gas changed as it was compressed. Well, P final, V final, that is going to be equal to NKT final. And P initial, V initial is going to be equal to NKT initial. So this is equal to 1/4 of NKT initial. Since N and K don't change as the system is compressed, it still has the same number of particles, right? And K is just a constant. That means that our final temperature is 1/4 of our initial temperature. So in order to keep the pressure constant, we had to drop the temperature by a factor of 4 in order to accomplish that. So as the gas is being compressed, we have to be taking energy out of the gas continuously in order to drop the temperature in order to keep the pressure constant, right? So constant pressure compression is actually pretty hard to do because you have to be constantly cooling the gas, which wants to be heated. Naturally, a gas that is compressed will heat up as you compress it because you're doing work on that gas, you're increasing its energy, and you have to be taking more energy out of the gas in terms of heat, right, to cool it down than you are putting in for work. So that's why our work value is so low for constant pressure, because we're dropping the temperature significantly as we compress the gas. Next, let's look at the isothermal case. In the isothermal case, temperature is constant, so pressure looks like NKT over V. All of the top stuff is constant, so pressure goes like some constant over V, right? This is going to look like a y equals 1 over x kind of a function as our PV diagram, which is going to go something like this. So it's going to curve up. The pressure is going to increase exponentially as the volume gets closer and closer to 0, right? As the denominator here gets smaller and smaller, the pressure is going to increase. And we end up at this point here as our final volume. And again, the area under this curve, so all of this area here that I marked with purple, is the work done on the gas as it is compressed. Note that this is a lot more work than was done in the constant pressure case. As we can see from our calculation, it's close to double the amount of work to compress the gas at constant temperature. And then we get to the adiabatic case. In the adiabatic case, the pressure isn't constant over just V. Pressure is some constant divided by V raised to the 7/5. So it looks like a 1 over V, 1 over volume kind of a thing, but the volume is, this denominator is getting bigger faster than it is in the constant temperature case, because I'm raising my volume to the 7/5 power. So this means that we should expect pressure to rise more quickly with decreasing volume than it does in the constant temperature case. So we might end up here. And we have all of this extra work being done on the gas as it is compressed adiabatically. And that red region represents that work. So again, we see that we get more work. We have to do more work on the gas to compress it adiabatically. And that's because if no heat is allowed to flow, we are doing work on the gas as we compress it. Doing that work on the gas will increase the temperature of the gas. No heat can flow out. The gas can't lose that extra temperature. So as we compress it, the gas heats up, and that heating leads to a larger pressure, which makes it more difficult to compress the gas, right? So we compress it a little bit, it heats up a little bit, the pressure gets larger faster than it would just from a normal compression, say an isothermal compression, which means it takes more work to compress the gas a little bit more, etc. And so the further you compress it, you end up doing more and more work than you would in either of the other two cases.